Hello everyone and welcome back to my channel. In today's lecture, I'm going to teach linear algebra and start with vector spaces, very basics of it. Linear algebra is a really vast topic and is really important in mathematics. It has great applications in computer science. It is extensively used in machine learning and has great application in economics as well. So it's a really important chapter and it's a very vast topic, so I cannot cover it in one or two lectures. So I will be releasing a series of lectures. Please do watch each and every video, and the series of videos will cover linear algebra up to senior year of your college and even some parts of grad school or PhD in mathematics. So please stay tuned. Also comment below or email me with any doubts or clarifications. So in today's session, we are going to discuss what complex numbers are. We will define them and see what all properties does it hold. Then we will discuss about the notation F. And to end our session, we will talk about lists and all the arithmetic operations that are possible on lists. So let's begin. So today we will start our discussion with complex numbers. And before diving into linear algebra, we should be familiar with theory of sets. So if you have any questions on that, please watch my previous video on set theory. And if you still have any questions, do comment below or feel free to shoot me an email because concepts of set is really important to understand linear algebra as a whole. So we are familiar with the set of real numbers and we denote the set of real numbers with this letter R. And for any real number, we know that if a is greater than or equal to 0, then square root of a exists as a number, exists and is also a real number. But if a was a negative number, then we don't know anything about the square root of a. So mathematicians came up with this number called iota, which is taken as square root of -1. And using this letter iota, we can find out square roots of each and every number. So if we have a number -a, we can write that as under root a times under root of -1 and then denote -1 as iota. So that could be written as iota times under root of a. And now this a is positive and we know that under root of a would be a real number. So let's define what a complex number is. So complex number is an ordered pair x comma y such that for all x and y belonging to real numbers, we write complex number as x plus iota y. And we need to be familiar with these symbols as well. I will keep on reiterating this symbol, but this symbol inverted a stands for all. And the symbol looks like E stands for belongs to. And anything written between parentheses always tells it's an ordered pair or even triplet or list that we are going to talk in today's session. So complex number is an ordered pair x comma y such that for all x and y belonging to real numbers, we write complex number as x plus iota y. This is how it is denoted conventionally. And if we were to talk how to write the set of complex numbers, then the set of complex number as a set builder form would be x plus iota y such that x and y belong to the set of real numbers. This is the definition and a really important thing to remember. Next, we are going to talk about addition and multiplication of complex numbers. So addition on the set of complex numbers C. So let's take two arbitrary complex numbers. Let's say we have A, which is x plus iota y, and we have complex number B, which is m plus iota n, such that we know that x and y belongs to real numbers and m n also belongs to real numbers. Then the addition of these two complex numbers a plus b would be x plus iota y plus m plus iota n. And now I forgot to mention this one thing. I'll give a quick brief. So whenever we write the complex number x plus iy, then x always denotes the real part of the complex number and y is always the imaginary part. So in this video and any other video, if I say real part, then it talks about this x, and whenever I say imaginary part, it talks about the iota y term. So here we add the real terms together, x plus m plus iota times y plus n. So this is how addition is defined on the set of complex numbers C. Let's talk about multiplication. I will also attach this PDF with the video in the description so that you have it as a reference. Again, let's take two arbitrary complex numbers, a equals to x plus iota y and b equals to m plus iota n. And to define this product of two complex numbers a, b, we have x plus iota y times m plus iota n, and we multiply it as we do a normal algebraic multiplication, x times m plus x times iota n plus iota y times m plus I square yn. In the last slide, we talked about iota being under root of -1. So we can say that iota squared will become -1. Similarly, iota cubed would be iota squared times iota would be, and we know iota squared is -1, so we know I cube is I, and then similarly I to the power 4 would be 1. To generalize this thing, we can write as iota to the 4n plus 1 would be under root of -1. Iota of 4n plus 2 would be -1. Iota of 4n plus 3 would be negative iota. And iota to the 4n would be 1, where n belongs to the set of natural numbers. You don't need to mug this up. If you know what the value of iota is, you can easily find the value of iota squared, iota cubed, and iota to the power 4 or any power. So now here, let's combine the real parts. We know that we have a real part xm. Looking at this term, it would become negative yn. So we write negative yn. This is all the real terms we got. And then plus, let's look at the imaginary terms. We have iota times xn plus ym. And we know that x, y, m, n all belongs to the set of real numbers. So this is how multiplication is defined on the set of complex numbers. Next, let's talk about the properties of arithmetic operation. Properties of arithmetic operations on C. So we know that the addition on real numbers is commutative, and so is the case with the set of complex numbers. So we know that for any real number a plus b is same as b plus a. Same thing for complex numbers. If we have two complex numbers x and y, then x plus y equals to y plus x. Also, the commutativity holds for multiplication. If we have A and B in real numbers, then AB is same as B times A. Similarly, for complex numbers x and y, the product x times y is same as y times x. And these are really easy to prove using the definitions of addition and multiplication. So I'm not wasting any time in proving these because we have many more complex proofs to go. But if you have any questions, do let me know in the comment section or feel free to shoot me an email. I will be more than happy to clear your doubts. Second, we will talk about associativity. Same as real numbers. So if we had real numbers A, B, and C, then we know that A plus B plus C would be same as A plus B plus C. And same thing holds for complex numbers. So if we have complex numbers x, y, and z, then x plus y plus z is same as x plus the sum of y and z. And similarly for multiplication as well, for three real numbers, a the product of AB times C is same as A times the product of BC. Similarly, for three complex numbers x, y, z, we have the product of xy times z is same as x times the product of yz. Next property we would discuss would be identity. So we know that for if a is a real number, then there exists this number 0 where a plus 0 is a. Similarly, for complex number, if we have alpha, there will be a 0 such that alpha plus 0 equals to alpha. And we know that for any real number a, we have a times 1 is a. We also have the same thing in complex numbers. For any alpha in complex number, alpha times 1 is alpha. Next thing we talk about is multiplicative inverse. So we know that for all real numbers, there would exist a number 1 over a, and we also know such that a not equal to 0. We know there exists a number 1 over a such that 1 over a times a is 1. Similarly, for any complex number alpha and alpha not equal to 0, there exists a number 1 over alpha such that 1 over alpha times alpha is 1. Since we talked about multiplicative inverse, we also talk about additive inverse. I'm mentioning all the properties of real numbers as well for a real quick brush up for real numbers as well. So for a in real numbers, we know that there exists a number negative a such that a plus negative a equals 0. The same thing holds for complex numbers. Alpha in complex numbers, there exists a number minus alpha such that alpha plus minus alpha equals to 0. The sum of alpha with a number negative alpha is 0. The last thing we talk about is distributive property. Distributive property. So for real numbers, we know that a times b plus c is equal to a times b plus a times c. The same thing holds for complex numbers. If we have three complex numbers x, y, and z, then x times y plus z equals to xy plus xz, where addition and multiplication are defined in the previous slides. And the proof of these are really simple. So I'm not wasting any time on these proofs. Just remember these identities, and they are really easy to remember as well because we already remember these identity for real numbers. One thing I want to discuss is the set R and set C. A lot of people have confusions regarding these two sets as which one is a subset of the other one. Because when we talk about sets, there is always a possibility that one could be a subset of the other, or these two sets are completely unrelated. So let's talk about these two sets a little bit more. So we know that the set R will be all numbers x such that x belongs to the real number R. But each of this number x can be written as x plus 0 times iota, which means that the set of real numbers is a subset of complex numbers, because the set of complex numbers contains all the real numbers in this form. So the ordered pair in which we define the complex numbers would become x comma 0. So each real number can be written as an ordered pair x comma 0 in complex number. So the complex number contains all real numbers, plus it would have other numbers in which the coefficient to iota would not be 0. So really important thing to remember is that the set of real numbers is a subset of complex numbers. A lot of people get confused. They either say that the set of complex numbers is a set of real numbers, or sometimes they think that these two are unrelated sets. But these are related sets, and the set of real numbers is a subset of complex numbers. Moving on to the next thing, we already defined addition and multiplication on complex numbers. Now let's define subtraction and division. So let's take two arbitrary numbers a and b belonging in the set of complex numbers. And from our properties, we know that for a belonging in complex number, there exists this additive identity negative a also belonging in complex numbers, such that the sum of these two numbers is 0. So subtraction of two numbers is defined as if you have a minus b, that is defined as the sum of a with the additive inverse of b. The definition remains same with real numbers as well. If you read the definition of subtraction in real numbers and change the term real with complex, it's the same definition. So the subtraction a minus b is defined as the sum of a with additive inverse of b. So that's why knowing the additive inverse was important. Now talking about division, we know that for all complex numbers that are not equal to 0, there exists a number 1 over a such that the product of these two numbers a and 1 over a is 1. So if we were to find the division of two complex numbers a over b, we say that that is the product of a with the multiplicative inverse of b. Obviously, b should not be equal to 0, then only the multiplicative inverse of b would exist. So this is how division in complex numbers is defined. It is really similar to real numbers. The next thing that we are going to discuss today is regarding the notation f. Some of you would have studied real analysis and some of you would not. It's perfectly okay to not have any background in real analysis, but in real analysis, we are introduced to one terminology of fields, and it has various properties. I'm not wasting any time in discussing fields more over here because it's a completely unrelated topic. It's a topic in real analysis. But if you want some more clarification, you can definitely let me know and I will have a separate video for that or teach you personally. So if you know a little bit about fields, then we know that the set of real numbers and the set of complex numbers are a type of field. And in general, fields are defined with are denoted with this letter F. So in my next videos or maybe in next chapter, whenever I write this F, it denotes all fields, which could either be the set of real numbers R or C. Basically, when we talk about F, we talk about fields. So all the properties of F will satisfy the properties of R and C. So it could either be R or C. It is not specifically to R or specifically to C. So instead of writing that alpha belongs to the set of real numbers C, in my next videos, I will say that alpha belongs to the field F. So since we already talked about multiplication, let's talk about the term alpha to the power m. So for all alpha belonging to F, the term alpha to the m is defined as product of alpha with itself m times. And one thing to know is that m is a non-negative number. So here if we have alpha to the m, we say it's alpha times alpha times alpha m times. So if we have alpha to the 4, we can write as alpha times alpha times alpha times alpha. We have it 4 times. And we know that this property of indices would hold true as well. Alpha to the m to the whole to the n would be alpha to the mn. And for two numbers alpha, beta, we have alpha, beta to the m equals to alpha to the m times beta to the m. Again, the proofs of these should be fairly straightforward. If you have learned them in indices, there's nothing different here. But if you have any questions or clarifications, let me know. But I'm not going in these small trivial proofs in details. The next thing that we are going to talk in today's session is lists. A really important thing, we need to know what a list is. We need to know the definition of the list because this term list is going to be used throughout linear algebra. And there is this word called a tuple. This is interchangeably used with list. A lot of mathematicians prefer it to call tuple instead of a list. So I generally call it list, but if you in your questions or in your book, if you see tuple, it means list. Please do not get confused. So let's define what a list is. So for m that is a non-negative number, a list of length m is an, and I'm writing in inverted quotes, ordered collection of m elements. I repeat, a list of length m is an ordered collection of m elements. And these elements could be anything: numbers, letters, name, places, sets, or any abstract item that you can think of. And in general, we denote or write a list as x1, comma x2, comma x3, so on till xm. This is how list is written. And from the definition of lists, two lists would be equal when their length is equal, such that they have same number of elements, all the elements are the same, and they have the same order. Really important thing is this term ordered collection. We always need to remember that lists is an ordered collection. So if they have the same length and same elements but in different order, the two lists cannot be equal. Also, if we are given a list x1, x2, and we don't know how many elements it has, if it has infinite elements, then this thing does not qualify for a list. The definition of list says that it has to be of a length m. So if you don't have a given length, it cannot be qualified. Any ordered collection without a specific length is not a list. This is really important thing to know. And just the way we have an empty set, we also have a list of length 0, and that thing is written as parentheses and nothing between them, just an empty thing. This is a list having no elements, so a list of length 0. And one thing is, lists and sets are very different. They are not the same thing. First thing in lists is it is an ordered collection, versus set is just a well-defined collection of objects. So the term ordered is really important. In sets, order do not matter at all, but in lists, order matter. For example, if you have a list 1, 2, 3 and a list 2, 3, 1, they have the same length and same elements, but they are not equal to each other since they have different orders. But the same thing, if we were to talk in sets, the set containing 1, 2, 3 and the set containing 2, 3, 1, they are same because the order does not matter in sets. So the first thing that matters is ordered. Lists are ordered and sets are not ordered. The second important thing is repetitiveness. In lists, if elements repeat, it makes sense. So 1, 1, 2, 3 makes sense. It's a list containing 1, then 2, and 3. And it is completely different from a list having 1, 2, 3. You can see clearly that the first list is of length 4 and the second list is of length 3. In sets, repeating elements does not matter. So if we were to make a set from elements 1, 1, 2, 3, the set would look like 1, 2, 3. So in sets, having repeated elements does not make sense, but in lists, having repeated elements makes sense. And the list 1, 2, 1, 3 also makes sense and is completely different from the first list written here. So the order matters and the repetition of elements also matters. The list would completely change if you change the order or add a repetition of elements. So very important distinction between lists and sets. A lot of people do not know the difference between these two or tend to confuse sets with lists and lists with sets. So I just wanted to make a clarification. The next thing that we are going to talk is the term Fn. So the thing Fn is defined as the list x1, x2 up to xn such that for all I belonging in 1, 2, 3 till n, x of I belongs in the set F. So this term Fn is nothing but a list of n elements such that each element belongs to the set F, which means it either belongs to real numbers or complex numbers. So we can say that this R2 is the ordered pair xy such that x and y belongs to R. And this thing is our Cartesian plane. And R3 is the ordered triplet xyz such that x, y, z belongs to real numbers, and this is the ordinary space. And we generally can visualize any list in R2 and R3 because we have objects in 3D, but anything greater than 3 such as R4, R5 and so on. So any n greater than equal to 4, it is really hard to visualize that thing, but you can just imagine it as a list containing 4 elements. So since we talk about this term Fn, let's talk about the addition in Fn. So the addition in Fn, let there be two lists, x being x1, x2, so on, and let y be y1, y2, so on till yn. Then the sum of these two lists, x plus y, will be the sum of each subordinate. So that means x1 plus y1, x2 plus y2, so on till xn plus yn. And the proof of this is really simple. We have two lists, x1, x2 till xn plus y1, y2 till yn. So now we know that this each term xi belongs to f and each term yi belongs to f. So we just add these, so on till xn plus yn. And looking at the definition, it means that x plus y is commutative, which means x plus y equals to y plus x. Again, the proof is pretty trivial. Since each element is in F and the property of commutativity exists in F, it also exists in Fn. You can easily prove this. Now, one thing when we talk about lists is this term 0. So 0 is the list containing all zeros, n zeros. And one thing to remember and really important thing is that the 0 on the left hand side is the vector 0, which represents the list, and each of these terms is the scalar number 0. Mathematicians in general do not write 0 to the n or denote the vector 0 by itself. They write the same 0. So it is really important to be able to find a distinction between these two. And most of the times it is clearly evident from the question that it is referring to either the vector 0 or the scalar 0. So whenever I talk about 0, I will always mention if it's vector or scalar most of the times. So let's just talk about one small example to make this example of 0 as a vector or a scalar a bit more clear. So we know that the additive identity exists for f, and similarly it also exists for fn. Again, very easy proof. So we would know that x plus 0 will be x for all x in fn. So now here, what does this 0 represent? It represents a vector 0. Because this x is a list of length n, you cannot just add a number to a list. A list can be only added with a list of equal length. So 0 is a list containing of all the number zeros of the equal length as x. Since we talked about additive identity, we will also talk about the additive inverse in f. In Fn. So for all x belonging to Fn, there exists a number minus x also in Fn, such that the sum of x with its additive inverse is 0. Again, this 0 refers to the vector 0 because sum of two lists is always a list of the same length. So this cannot be a scalar 0, it is again a vector 0. So most of the times when you see 0, you will be able to differentiate whether it's a scalar 0 or a vector 0. And if we had x as x1, x2 up to xn, then the additive inverse minus x would be minus x1, minus x2, so on up till minus xn. The next thing we talk about is the scalar multiplication. The term scalar means a number 1, 2, 3, 5, 10, minus 8, any number. We just use this term scalar, it's a fancy word for number, because now we are talking about vectors, and we will see in the later videos that vector multiplication is also a thing. So just a normal multiplication is said as a scalar multiplication. And we define that product as, for a number lambda in F and a list x in Fn, such that x is x1, x2 up till xn, we define the product of lambda x as lambda x1 times lambda x2, so on till lambda xn. And if we were to talk in R2 or R3, it is really easy to visualize. So if in R2 we had a point 1, 2, and if we were to have a scalar lambda equals to 2, then lambda times 1, 2 would be 2 times 1, 2 and 4. So we easily magnify the vector by 2. So 1, 2 would be lying, this would be the vector 1, 2, and the vector 2, 4 would be something like this. So it is in the same direction with double length. And similarly, if lambda would be something less than 1, then it would be, the vector would be shrinking in size. So this is all I got today. In the next video, we will talk about vector spaces and subspaces. So please stay tuned. This is going to be a long series of videos on linear algebra, a really important topic. I'll go in depth in each and every proof and each and every concept. Also, if you want me to solve some specific examples related to specific topics, do let me know in the comments section or email me at page.solver@gmail.com. Please subscribe to my channel and press the bell icon so that you get a notification whenever I upload the next video on linear algebra. Thank you very much for watching, and your feedback is highly appreciated. Thank you.